So, quiz on Monday, yeah? Okay, because we need to include the material which is covered to be covered by video only because I'm out on Friday, and that is the oxymercuration, hydroboration, hydrogenation reactions. Three different reactions. The first two are alternative ways to hydrate an alkene. All right. The first way is water and acid. Okay, standard hydration. The other two are some unique reagents, but they give the same type of outcome, hydration. The difference is one hydrates in one way and the other one hydrates the other way. Mercalnikov, anti-Mercalnikov. Standard, astandard, non-standard. Okay, in the video. In hydrogenation, you're just adding two H's to each carbon of the alkene. Go from the alkene to the alkane. Okay, hydrogenation or reduction. Stereochemistry involved there. Okay, good morning, guys. Let's get started. Any questions? Any remaining questions? Okay, we're pushing through the material. We'll pull things together as we can as we move along. Next week we will have lab lecture before lab. So next week we're meeting downstairs. I think that's what it says on the syllabus. We also have nomenclature video for alkenes. That includes the EZ terminology. Any questions there? Okay. And the EZ terminology will be on the quiz on Monday. Okay. There's one question on the stereochemistry warm-up. Because EZ is stereochemistry, how the group's oriented. The chlorine and the CF3 group can both be attached here, but one can be up or down compared to others. Okay, is this E or Z? Which takes precedence, chlorine or carbon?
Chlorine.
Chlorine. Which takes precedence over here, carbon or undrum H?
Carbon.
Carbon and chlorine, they're both on the same side, so it is Z. It's the same side. Right? Yeah. Okay, high priority groups on the same side. Z. E stands for opposite, right? Okay. EZ, but also stereogenic. That alkene is stereogenic. Okay, another questions there. Stereochemistry. Stereochemistry, very important. Thalidomide was the example of a drug where one enantiomer was good to treat morning sickness, but unfortunately the other enantiomer was given when it was started to be made and it led to birth defects. Okay, your hands are enantiomers. What are enantiomers? Mirror images that are different. Okay. If this looks in the mirror, what's it going to see? That looking back. Okay? Yes. All right. How do we know they're different? Okay. How about this here? Mirror image. If this looks in the mirror, let's see. Let's see that looking back at it. Yeah. I'm looking in the mirror. I see that looking back at me. Yeah. Are these the same or different? Same. The same. How do you know that? Because they're two identical paper clips, right? Okay. These are mirror images. Everybody agree? That looks in the mirror, see that looking back at it. Are these the same or different?
Different.
How do you know that? Because when you're like 1 year old, you figured that out. This will do something. This will go into the right hand glove. Okay. This one will go into the left hand glove. But this one will not. They're different. Mirror images that are different, we call these enantiomers. Okay? Well, why are these different but these not different? Those are mirror images. By the way, everything's got a mirror image. All right? Except maybe a vampire. All right? So that don't mean anything. Mirror image, yeah? Why are these the same but these different? The answer is plane of symmetry. If something has a plane of symmetry, and this does, because I can cut right through it, and I can have half on one side identical to half on the other side. Okay? It's a mirror plane, or plane of symmetry. If something has a mirror plane or a plane of symmetry, the mirror image will be the same thing. If it does not have a mirror plane, the mirror image will be different. Does my hand have a mirror plane? Can I slice right through it? No, I'll have a thumb on one side and no thumb on the other. What about this way? Could I slice right through there and make a thin hand, thin hand? Actually, no, because then I'd have knuckles on one side and palm on the other. So I can't slice that way either. There's no mirror plane here to be found. Thus, the mirror image will be different. Okay? Finding mirror planes will be important. I'll call that finding Waldo. Where's Waldo? Okay? If a compound has a mirror plane, it's not what? What do you call this? Chiral. When the mirror image is different, we call that chiral. Chiral, I think, is Greek for hand. Because your hands are this thing, and it's like hand. They're called handedness. And molecules can be like hands. Molecules can be chiral. Chiral meaning hands. What does a chiropractor do? He works on you with his hands or her hands. Manipulates your hand. That's where chiropractor came from. All right? Chirality. Handedness. Okay, let's look at this. Here we go. We have an outline. Chirality, my paragraph is there. I'm not going to read it to you. You guys can read? Yeah? I hear a yes. Good to know. Okay, let's look. Enantiomers, closer look at chirality. R and S enantiomers of 1 bromo, 1 chloroethane. Halfway down. A lot of the things we'll say are written up top. Here we go. 1 bromo, 1 chloroethane. Everybody agree that's the name of that?
Yes.
2 carbons. This is the 1 carbon. 1 bromo, 1 chloroethane. Yeah? Let's show the full stereochemistry here. So that's a tetrahedral carbon. And we can show this two in the plane. Let's put the chlorine forward. And what's going back on that carbon? This one. I'm drawing hydrogen. Let's draw it back. I'm going to draw it in and I'm going to draw it back. Now I drew that bond sort of up. In real life, that H and the chlorine were really eclipsed. They're both kind of like this. And this hand is right in front of this one compared to you. But I drew it a little bit more like this, so we can see the H, okay? But still, this one's forward, the chlorine's forward, right? And the H is back. So it's not exactly correct, but anytime you draw a structure, it's not going to be exactly correct, but it's pretty darn good enough, and there you go. Again, because it's tetrahedral, and this is not showing tetrahedral. There we go. What would the mirror image look like? Well, let's act like this is a mirror. What does it see over there in the mirror? It's going to see do those look like they're mirroring? I got a yes. Anybody else? I got a yes. I'm moving on. Everybody see that? Okay. There you go. Those are mirror images. Everything's got a mirror image though. Question, are these the same or different? Like your hands. Everybody agree that these are different? The molecules can be the same as well. Mirror images can be different just like these, and one will do something, and one will fit into a receptor or a glove, and the other will not, because of the way they are arranged. By the way, these both have the same name, agree? Okay? But the question is, are they different? Because they were the same, of course they'd have the same name. All right, those are mirror images. Do we have models of them? Well, let's see here. What colors we want to have these? Okay, chlorine green. All right, carbon over here black as usual. Bromine blue. This is supposed to be this one. You see how these are really, the green is right in front of the gray? I told you that. Okay. The H could have really been drawn down in front of that one, but okay. The H is gray is going back. The green, chlorine green going forward. Bromine and methyl are straight up in the plane of the board here if this was the board. Green, gray. If I agree that is that one, I'll put that one there. Let's see, which one of these mirrors that? Yeah, okay. That should be this one, the mirror. Bromine straight up, carbon black this way. Chlorine green coming forward, gray H going back, that's that one. Here we go. If this looks in the mirror, will it see the other one over there? Are those mirroring? Yes, they are. Okay. There are the two in my hands. They're the same on the board. Again, same or different? Different. Okay. How do you know they're different? Well, I could show you these two and I could say, hey, mirror images, same or different? And you would say same here. Hey, mirror images, same or different? Why are you saying different here? Yes. Where's Waldo? And the answer is there a plane of symmetry? How do you know there's no plane of symmetry? Well, let's hold it. I would hold it here. Can you cut my hand in half and you have one half the same identical as the other? No. What about here? What if I slice right through here? Slice it right through gray and blue, half gray, half blue. That's okay. But guess what? We'll have green on one side, black on the other. That's not a plane of symmetry. How about here? Right through green and black. I'll have blue on one side, gray on the other. You're correct. There's no plane of symmetry. And since there's no plane of symmetry, what does that tell us about the mirror image? Different. These are different. Yes. Another way to tell they're different. If they're the same, they should stack. Okay, you got saucers in your cupboard? Stack, 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 stack. Like 6 of them? Because they're all the same. Okay? That's called superimpose. What about our hands? Can I just stack 10 hands on top of each other? This one? No. The thumb is on the wrong side. I could turn it over, but now I got palm up. If this was identical, I should be able to take it and sit it right on top of the other one, and they line up exactly. Here we go. They don't. Thumb, okay? The thumb needs to be over there. What if I had another left hand over here? Can't you imagine that I brought it over, it would sit right on top of the other left hand? Yes. They don't. They're not superimposable. They're different. These are not superimposable. Okay, because let's try to sit them right on top there. Bam. Green and blue lining up. But the black and gray are not. Well, we can turn it. All right, now black and gray are lining up. They're superimposing, but guess what? Now the blue and green are not. They never will. They are not superimposable. What we have here is these compounds are not the same. It's 2 different compounds. What's their relationship? First off, are they isomers? Yeah, they have the same formula. What type of isomers are they?
Stereoisomers.
They're stereoisomers. Okay? Isomers. Different compound with the same formula. Basically, they have the same formula, so they're isomers. What type of isomers? There's only two types of isomers. Constitutional, what is that? Connectivity. Constitutional isomers have different connectivity. That means things are connected in different places. That means they're going to have a different name. Stereoisomers have the same connectivity. Wait a minute, did these have the same connectivity? Yes. Well, they were different. How do they have the same connectivity? They do, because look, it's a carbon with these four groups attached to that carbon. Carbon with the same four groups attached. It's not like the methyl is attached somewhere else, or the bromine is attached. Okay? The connectivity is the same. And thus the name is the same. The name of both of those compounds is what? One bromo, one chloroethane. Both of them have the same. The only difference how the groups are projected in space. They're connected to the same spots. They're stereoisomers. Stereoisomers have the same name. They only differ by some type of descriptor, like cis or trans, or R and S. Okay, we'll get there. Two types of stereoisomers. And antimers are mirror images, which are different. Because if they weren't different, they'd be the same. Okay? Diastereomers is another group we'll see is sort of a default. If they're not mirror images, but they are stereoisomers, we'll say they're diastereomers. Here's terminology. We'll use R and S here. D and L. Okay, back to these two guys. How can we distinguish them? They have the same name. We got to distinguish them somehow. Otherwise, I'd have to say, bring me one, and I'd say, no, I wanted the other one. You'd be like, well, why didn't you say that? I need to know a name. Tell me how to distinguish them. We distinguish these by a stereochemical descriptor, and in this case, it's RS. Let's back up a second. What are we looking at? Why is there no plane of symmetry? Because we have a chiral carbon. Probably in the paragraph up here. A chiral carbon is a carbon that, well, it has handedness. It has no symmetry. It's going to be a tetrahedral carbon with four different things attached. And that's what you have here. Tetrahedral carbon with four different things. 1, 2, 3, and the methyl 4. When you have such a carbon, there's no symmetry at that carbon. And if there's no symmetry there, then there's going to be no plane of symmetry, and that tells you that the compound is going to be chiral. Okay? A chiral carbon is a site of asymmetry. And we'll say this going forward. If a compound has one chiral carbon, it's going to be chiral. If it has more than one, it may not be chiral. We'll build upon that. Right now we have a chiral carbon. And basically the question is, how are these groups oriented about that chiral carbon? And there's only two ways it can be oriented. First off, it is two. It's more than one. But it's only two. And these are the two ways. The things can be oriented this way or this way. This orientation can be named with a letter, R or S. Here's how you do this. You give priorities to these groups, just like if you were doing E or Z. The four groups here, which is the highest priority? Bromine, chlorine, H, or carbon? Bromine. Bromine, so it's 1. What's next?
Chlorine.
Chlorine, 2. What's next? Carbon or H?
Carbon.
Carbon, 3. And this is, then you look at it, is the 1, 2, 3 clockwise or counterclockwise? Clockwise. 1, 2, 3, like a clock. And if it's clockwise orientation or configuration around the chiral carbon, we call it what? R. That's the R configuration. How about the other one? What's 1? Bromine? What's 2? What's 3? Carbon. By the way, when you do this, this is with the low priority group going back. What is the low priority group here? H, 4. Is it going back? Yes. Then we can do the clockwise or counterclockwise. Where's the low priority group? Is it going back? Yes, it's also going back. So with the low priority group going back, is the 1, 2, 3 clockwise or counterclockwise? Counterclockwise. And that is what?
S.
S. I think these are from Latin for R is like rectus, which means right. The clock is moving to the right. And S means what? I think it means sinister. It was a long time ago, people that were left-handed, they're sinister. Okay? I think that's where it came from. So, here's your name. This one is called R, and usually put that in parentheses. Name. I'm not going to rewrite the name. It'll be R there. And this one would be called what? S. And then the name. And the RS is a what? Stereochemical descriptor. And that's the only way you distinguish these stereoisomers, because stereoisomers have the same name otherwise. Now you can say, hey, bring me the R enantiomer. And I know which way we're talking about. That's just like if you said, hey, hold out your right hand. And I'd be like, oh, this one. Okay? Hey, hold out your hand. Right, which one? Hey, give me this compound. Which one? Okay? These are stereoisomers. We have chirality. There's no symmetry here. The mirror image is different. They're called enantiomers. Enantiomers have identical physical properties. By the way, what about enantiomers of this one?
Very same.
Let's see here. We can draw. First off, we know that's tetrahedral, right? I can draw here. Maybe I can do that. I can draw the mirror image. That mirror image. Yeah? Same or different?
Same.
How do you know those are the same?
It's a plane of symmetry.
Here we go. Carbon with 2 blue bromines, a gray H, and a methyl, yeah? Okay. Mirror image, yeah? What do we want to look for?
Plane of symmetry.
Plane of symmetry. Where's Waldo? Can you find a plane of symmetry?
Yes.
Cut right through here?
No.
No? Where at? How about right through here?
Yes.
Blue on one side, blue on the other. Cutting right through the black, so half a black on one side, half a black on the other, and half a gray on one side. There's a plane of symmetry right through here. Slicing right through the black, right through the gray, blue, blue. Plane of symmetry, so the mirror image is going to be what? Plane of symmetry, so the mirror image is
The same.
same. Okay? We can come back and we can make mirror image. Are these mirroring each other?
Yes.
It looks in the mirror, will I see that? Mirror images? Same or different? Everybody said they're the same, so they should superimpose, right? Blacks are lining up, uh-oh.
One rotation.
Blues are lining up, but no. But hold on. How about that? What do you see? They're superimposed. Those are the same thing. Mirror images that are the same thing. How many different compounds am I holding? One. I've just got two of the same thing. Okay? This compound is not chiral. Okay? Mirror image is not different. This is like the paper clips. Not chiral, not chiral. But the others, chiral. By the way, is this R or S? What's high priority group here on the apartment? Bromine or bromine? You can't do it. And if you can't do it, that right there should tell you it ain't R or S. There's no possibility. That's just like EZ terminology. If you can't do EZ, that tells you the alkene is not stereogenic. Okay? All right, enantiomers have identical physical properties, such as melting point, boiling point, dipole moment. I mean, any dipole here is going to be the same as over here. It'll just be just the opposite. It'll have the same intensity, but it'll be just the opposite. It's the same atoms, and they're connected all the same. And everything has the same relative spatial orientation. I mean, if you had two different enantiomers, they would have the same melting point, same density, et cetera, et cetera. So how do they differ? One is they rotate plane polarized light equal but opposite directions. That's because light is electromagnetic. Okay? And compounds have electrons, and the electrons will interact with the electric field of the light. And maybe that chlorine makes the light turn as it comes in here. The light is approaching, and the chlorine makes it go to the right. But this one, as it's approaching the chlorine, makes it go to the left. And so these molecules can bend the light differently. It's kind of a quirk of nature, but it makes sense. The one that rotates plane polarized light to the right, which is the positive direction, is called dextrorotatory, or D. If it rotates PP light to the left, the negative direction, that's the levorotatory, L. Now, R and S has nothing to do with D or L. R and S is based on structure on your paper or on the board. D or L is an experiment, and they're not related. Okay? Look at these two here. One of these rotates light one way and one rotates light the other. So one is D and one is L. But I don't know which is which, and I can't tell you because I don't have the data from the lab. But I know one is D and one is L. Because that's what enantiomers do. Enantiomers rotate PP light. I don't know which is which. Can I call that a DL pair though? I know one is D and one is L. Yeah, we can call that a DL pair. A DL pair of what? A DL pair of enantiomers. Okay? But I don't know which is which. Okay, next week we'll be doing this type of thing. Rotating the light here is called optical activity. And enantiomers are optically active. Enantiomers also interact with chiral objects differently. Is this glove chiral? Let's just like a hand. If I had another glove, it'd be held up here, and I'd say it'd have two different gloves. And we know they would be different, because only one of them would fit on the right hand. Okay, but these are also chiral. Basically, my hand is chiral, and the glove is chiral. Do these interact differently with the chiral glove? Yes, only the right hand fits into this glove. That's an example of number 2. My hands interact with the glove differently because the glove is also chiral. We said glove. This also gets to receptors. Okay? And that's why the drug thalidomide became toxic. Okay? Your body has receptors. Here's a receptor in your body. It's chiral. Here are 2 drugs. Okay? Enantiomers. Let's say if the drug binds to that receptor, it's going to lead to toxicity, birth defects. Okay? Now that's a left-hand glove over there. Which one of these will cause birth defects? The left hand. If fitting into that causes birth defects. Bam. Birth defects. By the way, how would a drug interact with a receptor? IMFs, hydrogen bonding, all those good IMFs. Okay? Bam, birth defect. If we gave this drug, it wouldn't fit in here. You'd be like, I can't get in there. So no birth defects. But maybe this one does go over here and do something good. Okay? That's getting at why thalidomide was toxic. It turns out that the bad one did something that it should not have been doing, or it was able to do it. Actually, enantiomers do have different smells, or can have different smells. How is that? Why would one hand smell different than the other? It's because in your smelling, your nasal, you have receptors. And they're actually chiral. They're like gloves. Okay? And one hand would go into this glove and give a certain smell, but the other one would go into a different glove and give a different smell. Okay? It's because your nasal receptors are chiral. And most enzymes are chiral. Okay. The thing that we will look more at will be number 1, the optical activity. This down here is more of the biochemical consequences that we could go on and give numerous examples about, as you advance and learn more. But we need to look at this more. And next week during lab, we will do that as part of pre-lab. Part over here, B, we'll look at in lab next week. Okay. Let's do a little bit more here, though. Optical rotation of 2-butanol. 4 carbons, like butane, and the OH group is on the 2nd carbon, and this can be called 2-butanol. All right, you'll learn alcohol nomenclature in Organic 2. We alluded to it on the first nomenclature handout. All right, well, let's show both enantiomers here. We can do this here. Lab reports, you got to be careful with your structures. You see how this carbon's connected to the O? All right, I'm seeing structures drawn a little bit not so good, and it all depends on which way you're flowing here, but like this, okay? you're going to have an OH group, make sure the oxygen is connected to the carbon. It just looks better, and it looks like you know what you're doing. Okay? That's a fine detail that I ask you to pay attention to in your structure, right? If I see how that just doesn't look good, all right? Let's have the O there connected. In fact, why don't you just draw the first atom there? Isn't the O connected to the carbon? Then you can add the H. And instead of drawing out a bond, a lot of times we'll just show the H sort of condensed. Everybody with me? Okay, so there's one possibility. Want to show the mirror image? Boom, boom, boom. It doesn't matter how you draw the H. I mean, I drew it over here. Are those mirroring? I mean, it might not be the exact same size. Mirror images? Same or different?
Different.
Let's do R and S. Because if one's R and one's S, that tells us they're different. Is that the case? What's the first one? I tried to group on this carbon here. Oxygen. Next, carbon or carbon? How do you do that? E and Z, same as that? I have to look at what's on the carbons. What's on this carbon? A carbon and two H's. What's on this carbon? H, H, H. Look at the first here. Do we have a winner?
Yes.
Yes. Carbon beats H. In the end, a longer alkyl chain is always going to beat a shorter alkyl chain. This is 2. This is 3. What's 4? Undrawn H going which way? Back. Going back. With the low priority group going back, is this R or S? Clockwise, which is what?
R.
R. How about this one over here? Does everybody agree it's a mirror image? Okay, I bet you a steak dinner, the other one's S. How do I know that? Because the mirror of R is, guess what?
S.
S. The mirror of my right hand is, guess what? The other one. The other configuration is possible. Yes. Real quick, oxygen 1, carbon another carbon 2, plain carbon 3, H in the back, is it clockwise or counter? Counterclockwise. S, you see? Okay, I like sour cream and butter on my baked potato. What about the third one? Is that possible? No, there's only 2 ways to configure groups around a tetrahedral carbon. And that's R or S. Okay, so what is that over there?
The same thing as the first one.
First off, is it 2-butanol?
Yes.
Is it a butane with OH on the 2? It's 2-butanol. So what is that?
The same thing.
Is it a third one? Do we have a Nobel Prize?
Yeah.
No, we do not. What is this? Let's do R and S. Because if you found a handout there, you could say, is that a right, left, or Tomo hand? I don't know what Tomo is. There's only right and left. If you find a hand that's not right or left, we need to really let someone know. Okay, what is this over here? Well, let's do RS. What's 1? Oxygen. What's 2? What's 3? What's 4? H. How's it coming? Forward. So what is this? RS. It's counterclockwise.
But the H is coming forward.
What do you do if the low priority group is forward? You just reverse your answer. And so what is that?
R.
R. These two are the same thing. All I've done is the OH is forward over here. You take this with the OH forward and just do that, then the OH will be back, and then it will be on more to the right. If you take this, okay, those are the same. They both are. They're just drawn differently. It's like this. Okay, I'm going to show you a hand. Here's one. That's a right hand. Okay. Right hand. Okay, now I'm going to show you another. Which one's that? Right hand. But the thumb's on the other side now. Do you see what I'm saying? How about that? What is that? Right hand. Okay? It's all the right hand. Those are both R. Since I determined it's R, that tells me it's R. And if that's R, this R, they're the same. Okay? So, here's something else we'll say going forward. What's the relationship between these two?
They're paired.
Enantiomers. Now, here I drew mirrored images. I won't do that going forward. Going forward, what we'll do is we'll keep the backbone the same, down, up, down, We'll just switch the projection from bold to dash, etc. If you keep the backbone the same and just switch your projection, you will go to the other configuration. And that's how we will do it going forward. Look at these. Are these mirroring each other? You can't see them mirroring as well. But you just have to know that, because what's the mirror image of S? R. Okay. They are mirror images. Okay. We know something about these. The specific rotation for S is 13.5. Okay, 13.5 degrees. That's the rotation of the TP light. And for R would be what? Negative 13.5, because enantiomers rotate equal but opposite. Okay, since we know this is negative, what can we also call this one? Negative. Negative, is that dextro or levo? Levo. Okay, L. That's an L. Small l, not capital. And this one is what? D. Okay, we can put that. Now it's possible to call this one L, 2-butanol. We could also call this minus 2-butanol. Or we could call this R, T-butanol. At this point, we have three different names that are possible. The first two basically mean the same thing, and the first two are only possible if we know that number. That's possible just by looking at structure. And in this case, R was L, and D was S. But that's just, those are not related. Sometimes R could be S. I mean, R could be D. Okay? These are not related, right? There you go. There's a closer look at enantiomers of T-butanol. Homework. Identify any chiral carbons in the compounds below. You can do that. Reactions. Which compound gives a chiral product when hydrobrominated with HBr? Will the product have RS configuration? Will that product be optimally active? Questions to think about.
Dr. Stevens,
Uh-huh.
for naming, is it possible to have both the R and the L in one name, or is it usually just one or the other?
Well, you could, because I mean, that gives you more information. Yeah, sometimes you include both. Since they're not related, yeah. Stereochemical descriptor. That's the only way to distinguish stereoisomers. Because otherwise they have the same name. Both of those, all those on the board were 2-butanol. It's like these. They're both called hand. But one's called right hand and one's called left hand. Right and left is a descriptor. Okay, Fischer projections. First off, assign RS to each compound below. This is RS. I assume we have a chirality because that's when you do RS. Do we have a chirality?
Yes.
Tetrahedrocarbon. Okay, small molecules right now. Plenty of examples with bigger molecules. RS configuration around this chirality. What's high priority group? Chlorine. Next. F for carbon. Carbon. Then H. Okay, is the low priority group forward or back?
Back.
It's in the plane. It's on the board. Flat on the board. How do you deal with that? Because if it's forward, we know we can just reverse. You need to look at this with the group going away. Or forward and reverse it, but let's look at it with the way. Let's look at it as if we're over here. Here's the carbon. If I'm over here, is the H going away from me?
Yes.
Here's the carbon. Yes. What do I see? Similar to Newman. A little bit. But we're looking at just one carbon, not down a bond. Okay? Fischer projections, we do crosshairs. And here's the chiralcarbon. Okay? And when we do crosshairs, it's as if the things on the sides are coming out. And the things going up and down are going back. Methyl straight up, H gray going that way, chlorine green coming forward, F we'll call blue going back. Okay? I'm over here. You see if I'm over here, the gray's going away? Do you want to see what I see? See if I'm over here, the gray's going away? I'm holding it as it's going away from me. That's what I see over there. That's why I'm standing over here. Okay? When it's going away, chlorine is 1, F is 2, and methyl is straight up. Green, blue, black. So is the green, blue, black going which way?
Clockwise.
Green, blue, black. It's going clockwise. With the H going away, it's clockwise. So what is this?
R.
It's R. But let's look at it this way. What do I see? This is like this. And this is drawn on the board like this. Whenever you see crosshairs, it's like that. That is, the things on the sides are coming forward. And the thing at top and bottom are going back. Okay? Does that look like that? 2 on the side coming forward? Yeah. Whenever you see the crosshairs, you have to think of it like that. You really don't have to because you can just work like that. That's implied. So, what do we see over here? This is, again, similar to Newman. If I'm over here, what's going straight up on the board from over here?
Methyl.
The methyl. Okay? It's going straight up. What's going down towards the feet? It's the H. Now, if I kind of lean a little bit and put the ground like this instead, I'll lean back. The H is coming down to the ground. Okay, going away from me down to the ground. Here. Going away from me down to the ground. Isn't that going away? Yes. See how it's going away? It's implied. If I'm over here, what's on my right towards you? Chlorine. And what, if I'm over here, what's going back? F. There's the compound drawn in a Fischer projection. This is very powerful. It's a better view. Now we can do R and S as a second step. What's high priority? 1, 2, 3, 4. Now, forget about that drawing. Let's focus on this drawing. How is the H, forward or back? Back. With the H back, what is the 1, 2, 3? Clockwise. And the answer is R. We did this because the H was in the plane, not forward or back. Now you may be able to get R somehow by looking at this. Whatever works for you, do it. My recommendation is put this in a Fischer projection, then clear your mind and start fresh with the Fischer projection. And now it's easy because it's more defined. But guess what? We also need to be able to draw Fischer projections for other reasons. Okay? Compounds in more than one carbon, such as the compound you made in lab last week. You look at it, it's got 2 carbons. I'm not going to be here on Friday. I'm seeing now that the lab report should not be due on Monday. Because we're just now getting into Fischer projections. The lab report will thus have to be due when you come to lab next week. All right? Is that okay? All right? Because we need to talk about Fischer projections. Please be doing some reading. You've also got the video replacing the Friday lecture. Alkene reaction, hydroboration, oxymercuration,